Alrighty, so I was assigned enthalpy number 2, which is going to follow number 1, obviously, and this one covers bond enthalpy specifically, or chapters 7 or 10.7 and 10.9 in your textbook. Okay. So basically what's happening during bond enthalpies is you are ripping apart the bonds that kind of holds together the structures of the reactants to separate them into individual atoms. So no matter what the formulation is, you got all the bonds to create those individual atoms. From there, you're going to create new bonds. Our bonds are formed to create the products. So when you see the equation, you've got the reactants and the little arrow and the products. And that's basically what's going on here. So you're taking the reactants, you're breaking up the bonds that kind of maintains the structure, and then you're going to create the products. And those resulting products are going to have these formed bonds. And because you are taking these bonds, it requires energy to break them because it doesn't just happen naturally. You're going to have to put work into it, and it separates those bonds finally into those individual atoms, which is why the arrow is going up, because it requires work. However, when bonds are being formed, it releases energy. And so that's why that products arrow is so large, is because it releases all that energy to get down to the products and to create those eventual formations. All right, so basically you're ripping the bonds, you're sticking them back together in different arrangements, and then you're going to take the difference, which is what this bottom equation is describing. So the total enthalpy of the reaction is going to be the sum of the entropy of the breaking bonds and then subtracted by the enthalpy of the formed bonds. Okay, so bond enthalpy. Bond enthalpy pretty much is bond energy. It's going to be specifically the energy it takes to make 1 mole of bond of a certain type of bond. Now, these certain type of bonds, it can be anything really. It can be a carbon-carbon, it can be a hydrogen-hydrogen, usually not, kind of rare, but or you've got a carbon-hydrogen or an oxygen-carbon, like it says right here on the slide, or it could be a carbon-oxygen, and it really doesn't matter because there are infinite options. This kind of creates the perfect setup and the perfect equation to find enthalpies of whatever equation you need, which is super, super helpful when it comes to like really large ones, because you can break it down, say, this is the structure, I'm taking out all these bonds and creating this, and I can find the total energy enthalpy of this reaction. All right, in correlation with that enthalpy and that energy, we have bond strength. So bond strength, as it says in the slideshow, is the greater the bond enthalpy, the stronger the bond. And vice versa is also true. So the smaller the bond enthalpy, the weaker the bond is going to be. And if you remember from previous lessons, we've talked a lot about how size also correlates to strength. So when it's a small bond, when it's a short bond, it is stronger because it's like less likely to break. Think about, say, a dry noodle, right? You've got a piece of spaghetti that's really, really long, and it's pretty easy to break. But when you go to a smaller piece, let's say you've got like a hardened piece of ravioli, right? It's smaller, it's thicker, and it's stronger. And so you're gonna have to crush that instead of just breaking it. Maybe you're really strong, but that's how I like to think about it. Okay, and so if you remember that, you can be able to relate that the shorter the bond, the stronger it will be, and the greater its bond enthalpy will be. And so the longer the bond, the weaker it's going to be, and the smaller the bond enthalpy will be, which will be reflected in charts. So the moral of the story is basically that everything's going to be connected. If you kind of utilize all of that history that you have in chemistry, you'll be able to remember and apply it here, and everything kind of starts making sense. Okay, so far we've kind of gone over a few different equations, and we've already learned about some of the reactions by this point in the lesson, and that's basically just the individual enthalpies of the reaction, and you can add those all up together to create this ultimate enthalpy of multiple different reactions. which can be super helpful if you've got a really complex one. Or we have the second one, which is going to be enthalpies of formation. So enthalpies of formation is kind of the standardized one. It's where you take the enthalpy of those products and subtract the reactants. And if you'll notice here, this is where bond enthalpy is kind of strange, because bond enthalpy is basically taking the reactants and subtracting it from the products. And so we have on the bottom one, we've got those enthalpy of the bonds breaking, subtracting by the enthalpy of the bonds forming, which kind of contradicts the other one, but this is just how bond enthalpy works. So if you recognize that, you're going to want to remember that, because that is super, super important moving forward. Being able to differentiate between enthalpies of formation and the bond enthalpies, because there is such a stark contrast between those two. Okay, so there's a couple different things that you're going to want to remember regarding bond enthalpies. First off is that they're always going to be positive, because when you break bonds, it requires energy, like we talked about earlier, how that arrow was going upwards because it required the energy to break apart. It doesn't naturally happen. The second thing is that energy is released when bonds form, which we touched on this earlier, but this is super important because this is how life works, really. Your body, plants, animals, they all use this reaction to create energy. And so when those bonds finally come together and those products are made, we have an increase in energy of the system. Also, very important, it is the approximate answer, it's the average, not the specific bond enthalpies that we see in charts. So when you see a carbon-carbon bond and you see that specific number, that's not actually the number, because it varies depending on what's being formed and what's broken. That will kind of determine what that enthalpy is. And we've talked about that a little bit before. All right, so this is what you're going to be looking at when you see bond enthalpy charts. And I just wanted to put up a visual because I think that's super helpful. So when you approach a question, you're going to often find a section of this chart, whatever bonds apply to that specific problem. And so you'll see if you've got a CO2, right? You're going to see a carbon-oxygen bond. And usually that's going to be a double bond because oxygen goes on both sides. Or if you've got a CH4 bond, you're going to have four hydrogens surrounding a single carbon. So yeah, if you've got a carbon CH4. So you'll have 4 different CH bonds. So like just looking at that and applying to what you know, taking that equation that we've already kind of talked about, you can find the bond enthalpies fairly easily. Just follow the structure, make sure you get your numbers correct, and you should be good. Another thing I want to touch on here before we leave to the next slide is this idea of multiple bonds. And this can be super confusing, but if you notice that this carbon-carbon bond, right, it's a double bond. But if you go up to the single bond of the carbon-carbon bond, it's 348. So naturally you'd assume, well, yeah, just multiply that by 2. However, you can't do that because of the reaction and their connection. They have a naturally stronger bond because it's that double bond. And so their enthalpy is actually going to be different. So you can't just multiply 348 by 2 because you're going to get a wrong answer. You're not going to get 614. You're going to get a very different number and your results are going to be skewed as a result. And so you're not going to want to do that. Just be very, very careful. Don't multiply by 3, don't multiply by 2, multiply it by 1 or however many you have of that specific bond. But if it comes to double bonds or triple bonds, do not multiply them thinking that you can just multiply single bonds, because that will be very unfortunate. Okay, now we've got a practice problem. I know, it's very exciting. Okay, so we're going to be finding the enthalpy of a reaction through bond energies. So at this point, I'm going to put up this equation. Let's see if I can move this down a bit. Yeah, perfect. Okay, we are going to be taking, I guess you guys might see. All right, you're going to be taking CH4, and we already see that this is balanced, so you don't really have to do anything. But if you guys want to pause this right now, then you will be able to do it on your own. You can try it out. If not, you can just stay on and we'll go through it. All right, that should have been enough time to pause it. If not, you can just pause it while I'm talking. So we're going to take this equation that we've already talked about, and we have this average bond enthalpies. Like I said earlier, you'll have this little chart. No matter what problem you're looking at, you're going to have the related bond enthalpies. Okay. Oh, oops. All right, so we've got our broken bonds. So that's gonna be our first step. You're gonna want to take your broken bonds and see how many you have. So the CH4, you're gonna have kind of like a crisscross, right? And so you're gonna have a carbon in the middle with 4 hydrogens on the outside, which means that there's gonna be 4 carbon-hydrogen bonds, which is where we've got the 4 right there. 4 O2, you guys kind of already know, it's a classic linear shape. And so you're gonna have those 2 O2, but because there's 2 of them, right here, signified by the moles, you're going to multiply it right there. And then you're going to take your formed, which is the CO2, and CO2 has the carbon in the middle and the double bonds on the outside, like I was talking about earlier. And you've got 2 of those because they're on both sides. And then you've got your H2O. So you've got your carbon and then your hydrogens on both sides. But you've got 2 of those, so you're going to multiply that by 2, so you're going to get 4. Which is why it's right there. Okay, these ones just straight across, you've got CH bonds is going to be 413 kilojoules per mole, and oxygen is going to be 495, which is where you get the 990 kilojoules, and then you're going to have your formed CO 799. You guys can kind of see it, but you've got your 463 right there. That's supposed to be hydrogen. That's okay. Oh, sorry guys. Okay. So I'm gonna move this up because you can't see the answer. All right. So you've got the enthalpy of your total reaction is going to be those bonds that have broken. Remember, it's not going to be the products this time, subtracting. It's going to be the bonds that are broken, which is going to be that 1652 plus 990, and then you're going to subtract your forms, which is going to be 1598 plus 1852. So ultimately, you're going to get the answer at 900, or what? Negative 808 kilojoules per mole. So if you did that, good job. Okay, so we've got a second practice problem as we're kind of moving forward, as we're dealing with fuel density and fuel values. So this is going to be super important going into the test because there wasn't very much emphasis on it in lecture, but it did play a big role when it came to SmartWorks or practice problems or stuff like that. Okay, so we're going to take ethanol, and ethanol is going to be that CH3, CH2OH. You may also see this as C2H5OH. There's a lot of different variations because there's so many hydrogens and so many carbons, and there's a lot of different arrangements that you can make. And so we're going to just do combustions right here, which is what you're looking at. And then you've got your methane right here for the CH4. All right, and then you're going to want to make sure, pay super careful attention to what state the element or the formation's in, because that formula could be in liquid, and that's going to have a different enthalpy than it would have in gas form and things like that. So pay attention to what they give you, and then we'll work from there. If you guys wanted to work through and see if you can go through this problem, just go back to this slide. You can screenshot it, do something with it, and then utilize that to solve for these equations, see if your matches up. If they do, good job, you're on the right track. Okay, so these ones are already balanced. So that's going to be your first step. Make sure they're balanced. If not, your results will be false. And then use the same equation that we were talking about before. Enthalpy of the reaction is going to be equal to the enthalpy of the broken bonds minus the enthalpy of the formed bonds. So that's how I'm getting that negative 1234.7 kilojoules per mole. And then ultimately you'll get a negative 802.3 for methane. All right, so you're gonna take that, and unfortunately, we do not sell in moles. That'd be kind of ridiculous for buying gas or anything like that. So instead, we're gonna kind of put it down to a reasonable value, and that's gonna be in grams. So your fuel value, the difference between your fuel value and your fuel density is just gonna be, fuel value is kilojoules per gram usually, it also might be joules per gram. It's just energy per gram. Fuel density, on the other hand, that's gonna be out of milliliters. So you could have really any energy, but as long as it's out of milliliters, you'll know that's gonna be fuel density. So we've got right here, you're just gonna take your enthalpies and you're gonna set it equal, do that dimensional analysis, and divide it by its molecular mass. You can also just go straight to dividing by molecular mass. You don't really have to set up those fractions if you understand what you're doing. But ultimately, you're just going to get the negative 26.8 kilojoules per gram, and the second one will be negative 50.02. What's super interesting about fuel values, and this is why you need to convert it to grams to kind of understand what you're looking at, is because at first you think, okay, ethanol is clearly going to be more efficient because it's creating more energy, right? In comparison to methane when it's kilojoules per mole. However, when you convert it to kilojoules per gram, you see that ethanol is actually creating negative 26.8 kilojoules per gram in comparison to the negative 50 that you can get from methane. So in this case, methane is actually going to pull the win. Okay, so overall this may seem a little unnecessary to learn about. However, for those of you going pre-med track or med school, anything like that, you might be going PA school, but you're still gonna wanna know this entire process because it's so important to life. And I touched on this a little bit earlier, but ultimately the body runs on ATP and the exchange from ATP to ADP. Right here on the slide, it talks about the human body is powered by the constant breakdown of this adenosine triphosphate. And as it's breaking down, which is what you're seeing right here in the diagram right here, you're seeing all of those oxygens and the phosphates. All of those are kind of getting reorganized and pushed around. And that's what's going on. You have those bonds that are breaking, and you see those bonds that are forming in the body, which is creating new products and kind of destroying that reactants. And so the human body is powered by this constant breakdown, because we talked about as bonds break, they require work. But this might seem kind of like counterintuitive. Like, wait a second, like as it's breaking down, why would that create energy? Well, as it's breaking down those things, it's naturally going to create lower energy products. And it's these low energy products that are creating abundance of net release of energy. And that release of energy is what's powering your body. And so it's not necessarily the breakdown of adenosine triphosphate that is creating all of this energy for your body, but it's the forming of ADP following the breakdown of ATP that is ultimately going to help you function. And that's right here. The result's going to be a super happy and healthy body, and everything's going to be working perfectly. That's the hope. But it's super important for life in general, which is why you should know about it. Okay, so if you are still confused, you can go through and watch. It's probably my fault, so I'm sorry. But there are a lot of online websites concerning enthalpy in general, or the reactions, or even the application when it comes to bodies or plants or animals. And you can look into that, because there's a lot of different reactions when it comes to enthalpy, because everything has, or a lot of things have energy and transfer of energy. And so if you need specific guidance on ATP to ADP or anything like that, there are websites, there are videos, just reach out and you'll be able to find some. If you don't find anything on your own, there are also other resources. You can talk to TAs or other students about this. You could contact me through this through Learning Suite or something like that. And I'll be happy to help you. If not, you can also just rewatch the lectures. And that's been super helpful for me because if you go back and rewatch the lecture, you'll be able to reteach yourself and kind of digest everything that's coming in. Or you can just go through the PowerPoints themselves. And if you go through the PowerPoints, you can work through the problems. We can also go back and if you go back to, sorry, forgot about this. If you go back to this chart, you can look at different equations and you can create them your own and then look up the answers. And getting that practice in will be super helpful to remembering how to do bond enthalpy and figuring it all out. So ultimately, I hope you guys kind of understood what's going on. If not, there are resources. But yeah, that is bond enthalpy.